All right, folks, welcome to Cisco Live. We're so glad you're here, and I'm so glad that this is the first session for some of you. So we'll make sure to make it a really good one. This is Optical Networking Fundamentals. I'm Brad. This is my colleague, Kent. Optical people do not know routing, and routing people do not understand optical. It's a tradition as old as time itself, and a very big reason for why you are here today. All these optical concepts, until this very moment, are merely the stuff of dreams. But if you're willing to set aside your distractions for the next 60 minutes and join Kent and myself, you will walk out of this room with a brand new confidence to chart a new course and possibly even a new career. Kent and I, we're both a part of the Mass Scale Infrastructure Group.
Right.
We're technical solutions architects, so we've been on the team for a few years. But I will tell you that our careers are the very opposite, the mirrors of each other. Since we're in Las Vegas, I'm willing to take a bet that most of you in the audience are a lot more like myself than you are like Kent. I spent the last quarter of the century building routing networks all over the world. Several years ago, I got involved into this optical technology, and that's where I was able to meet Kent. So Kent, tell us a little bit about yourself.
Well, Brad, thanks for the introduction. I'm just kind of the opposite, right? I started in the optical domain, got partnered up with people like Brad, and we're really coming together to develop solutions for our customers, for Cisco, to architect as well. So very interesting that the two worlds are coming together, just like anything, right? As the technology evolves, things get smaller and they can come together with less equipment and less infrastructure.
So for myself, I got to learn from the very best. And we've put this session together so you can learn from the very best on your own, right? So with that, a little bit of logistics here. Here's the WebEx app. Go ahead and join the room. You'll be able to join the discussion, ask questions. I think these go on past the event itself. If you want to get a hold of us and get in touch with us, our emails are, I think, at the end of the presentation. We'll be able to talk to you after the session as well. This is the brief summary of the contents for today. Essentially, what we're going to give you is a crash course in DWDM. We assume you know nothing about optical, and we will give you the very best and the most necessary components that you're going to need to go forward. So with that, the first time I heard the term gray optic and colored optics, I was surprised, coming from the routing world. To me, they were always the 1310, 815 nanometer GBICs or pluggables that I would insert into my campus network, and that's that. And so gray optics, colored optics, to me, I did not know what those were. Maybe some of you do not know what those are today, but we will be sure to explain what they are. I also have found out that a layer 1 skill set is very different from what we're used to in the routing world. And the fiber optic technology learning curve can be steep. Kent, you've dealt with guys like myself for a long time. What have you found?
Well, working together, you can learn the DWDM piece very well, right? I mean, it's not anything greater than you've already learned in the IP domain, but if you can really bridge the two together, you're going to be very much more successful in your industry and at your companies. The thing, Brad, is when we talk to our customers, they're not getting any more people, right? They're actually losing people, the networks are growing bigger, and so really if they can diversify the skill set and know more and bring technologies together, they're better off. I think the last bullet on here is sometimes we think these networks are very costly from a DWDM perspective, but really the true cost is that optical fiber that is in the ground, right? That can only go in once, and that's where the cost is. And what we're really doing in a DWDM environment is maximizing that fiber that is in the ground. So keep that in mind. That's really what we're doing. That's what we're trying to do with this technology.
I think the picture that you see here summarizes my experience and maybe even yours. I've seen diagrams like this, and I look at them at times, they don't make sense, and then they make sense, and then they don't make sense, and the optical guys explain it to me, and still there's fog in my mind. So that's,
Brad, we'll spend some time on that diagram here.
Yep.
Yeah.
Okay, so Kent, tell us, what is DWDM? I've heard wavelengths, frequencies, channels. What are they?
They're all the same thing. Every one of those terms, it means the exact same thing in this environment. So don't get too worried about that channel, wavelength, frequency. They can mean the exact same thing. Really, all we're doing is putting different wavelengths or frequencies, right? And we'll talk about that here in just a second, onto a fiber or a fiber pair, right? So each wavelength frequency channel is independent of each other. That's all we're doing in this environment.
Kent, coming from the routing world, it is easier for us to think about these channels as individual either VPNs or maybe VLANs going through a trunk. Is that a wrong analogy to be thinking about that in
Very
the...
similar. Very similar. That's exactly right. You're in the electronic domain though, right, Brad?
Yep.
This would be in the optical or with photons. That would be one of the differences.
Fantastic. All right, what is it that we need to know about DWDM or WDM that is different from Ethernet or IP?
Well, one of the beauties with it is agnostic. It doesn't matter if it's an Ethernet service coming across that wavelength or a SONET service, fiber channel, any of those, it doesn't know nor care inside the optical infrastructure. So that's one of the beauties of it. I think the other thing to think about, as the service bit rates increase over time, it may have been 10 gig E 3 years ago, now it is 100 gig E, and we can carry that across oftentimes the exact same infrastructure. So that's the beauty of DWDM, really being agnostic and in many ways bit rate transparent.
Okay, I think one of the other terms that keeps kind of getting bounced around and always used interchangeably, there's DWDM, I heard CWDM, DWDM. It's an alphabet soup. How do we make sense of that? What do they mean?
We oftentimes mix them all up, right? WDM, DWDM, and there's even a CWDM here in the middle. It's not very prevalent today, but let's kind of start back in the history of time. WDM was deployed to multiplex 1310 that was originally deployed with 1550 wavelengths. So the fiber was very scarce. We said, hey, we've got two frequencies. We want to multiplex those together, oftentimes with just passive filters in those early days, and we generally call that WDM. CWDM and DWDM kind of came about really at similar times. CWDM was attractive at one time because the lasers were less expensive. You'll notice the 20 nanometer spacing between each adjacent channel. That allows a lot of width or play in that DWDM carrier coming out of the interface. As the DWDM...
hang on 1 second here. So wavelength division multiplexing, what does C stand for?
Coarse.
Coarse, okay,
Coarse.
gotcha.
Dense is the D over here. But what has happened nowadays is really the DWDM interfaces are just as prevalent. CWDM is really not even deployed too much, maybe in some access networks, you know, campus networks that it was there originally is deployed. But DWDM, the cost of came greatly down. We're generally dealing with the C band today, but the L band we'll look at here in just a second is becoming a little bit prevalent where fiber is scarce and the number of channels is increasing. Maybe long haul backbone networks.
I got you. So CWDM, that's wider channels, but I can have fewer of them. The dense wavelength division multiplexing, tighter channels, but I have
Correct.
Up to what, 40, 80, 96, depending on what kind of filter I'm using. Question, can CWDM talk to DWDM?
Not generally, not a CWDM wavelength source cannot generally go into a DWDM infrastructure because it doesn't have a very tight tolerance on the transmitting laser frequency. The opposite, though, does work, and in the past we have did a lot of DWDM channels inside of a CWDM infrastructure. Maybe it was a 1530, 1531 DWDM channel that we could go across a CWDM filter set because the frequency coming out of that transponder or source was very tight and it would fit perfectly into a CWDM infrastructure.
Okay, good.
Brad, the other thing I wanted to note here is the ITU standards. We've got these listed throughout the presentation, and ITU-T has a lot of different standards. We've referenced these a couple places throughout the deck, so be sure to go back if you'd like some more information. A lot of this is standardized by the International Telecommunications Union.
Well, since we're in the ITU-T grid, we talked about gray optics, right? 1310, 850, and now we're talking about colored optics. So what do these colors, they represent frequencies, right?
Right. So ITU-T has actually come up with a gridded infrastructure, if you so choose to use that. But what we really wanted to note on this slide, team, is the spacing differences of the wavelengths is at the top, so 15, 28, 77 nanometers, that's a wavelength, means the exact same thing from a frequency in a terahertz domain. So that's why I said originally, when we kicked off the presentation, that wavelength, frequency, channel, they can all mean exactly the same thing. Here is the comparison between the two. So when we're at the frequency domain, each of the standard wavelengths is 50 gigahertz apart. When we're at the, up here at the top, with the wavelength, we have 0.4 nanometers between each center frequency. So this is with a fixed grid, a standard grid system. Nowadays, a lot of the networks are variable grid or flex grid, and we can do a lot of different channels and not necessarily have to follow this gridded infrastructure.
Good stuff. All right. Welcome to the Optical Fiber Crash Program.
Yeah, this is...
Kent, I've seen many different types of fiber, and from a routing person, we're talking to the fiber plant folk, we cannot make sense of what does it mean? There are different standards, there are different alphabet soup numbering.
Yep.
How do we make sense of the fiber that our audience is likely to see out in the field?
Well, first of all, these are all single mode fibers that are deployed in the outside plant. These are fiber types, and again, they are defined by ITU, and those GDOT numbers are posted. What we've did on this chart, though, team, is try to give you a quick reference. The number 1 at the top, that means that is the most widely developed or deployed fiber type out there. That would generally be an SMF-28. But oftentimes we say SMF-28, just like what your analogy?
Yeah,
Brad?
Xerox.
Xerox, yeah, we meant
Kleenex.
copying. But actually, SMF-28 is a fiber type. It is the original generally that was deployed. We list some attributes for each of these. The second one that's most commonly deployed, especially in the longer haul networks out there, is non-zero dispersion shifted fiber. And we'll give you some analogies of what it's good for. And over time, we thought...
Dispersion, never heard that before.
We're gonna go to that.
Okay.
We'll go to that. Over time, we created different fiber types to try to solve some problems. But really what I'll tell you is the original fiber that was developed is actually the best fiber to use. So SMF-28 is that fiber type. That's a particular vendor, but it's really GDOT 652. Works beautifully for DWDM infrastructure.
Okay. All right, now we talked about that ITUT grid, right?
Yes.
And you talked about the 1515 nanometer frequency. What was the specific reason that frequency was chosen, frequency range?
Well, the main reason, team, and I'll kind of highlight it right here, this black line is actually the attenuation or the loss per unit of fiber. So you'll notice right in here is the least amount of loss or attenuation. So that's why this was picked for DWDM infrastructure. CWDM kind of stripes through many of these as well, but from a DWDM perspective, we are out in here, which is the lowest attenuation or loss in the spectrum inside the fiber.
So I noticed, yeah, 1310 was right there also in the low mark, and
Right.
I definitely do not want to be in the 1400, right? Because that's where my loss is
Yeah, really not gonna work very well inside of this area right here.
Okay. All right, so a little bit more on the grid itself, Ken.
Yeah, let's look at this. So first thing to think about, the first window that we started deploying with optical technology was multi-mode, 850, right? So it's way out here. So then we'll kind of start, the second window of deployments was around 1310. So it's right here. And then really the third window was the C-band right here. And then the fourth window that is starting to become deployed more and more is what's called the L-band or the long band. C is for conventional. And then over here in the 1310, this is the O-band for the original deployment. So, and then, from a fifth window right here, the industry is looking at this S-band, but it will require some different investment, but always to increase the amount of channels on an optical fiber path, right? So we can combine these bands together in some cases. So what you'll see is C plus L, and you're getting sometimes double the number of channels or wavelengths by combining C and L together.
So C-band is the band that the audience is more likely to
Yes.
see out in the real world. Sometimes L-band and S-band maybe
It would
in
be
the future?
95% C-band team, especially in metros. You know, this is where the lowest cost deployments would be, is right in here.
Good stuff. Okay, I almost interrupted you about that dispersion. What are the transmission impairments?
Well, let's
that
look
you
at three
encounter?
of them right now, and we'll talk about attenuation a little bit here in a second, but this is common just like voltage drop, right? So resistance in an electrical cable, attenuation is the resistance equivalent in an optical fiber cable.
That's why we can only go, what, 100 yards or 100 meters and with the Cat5 cable?
One of the reasons, yes. Chromatic dispersion, and all these transmission impairments are linear generally. Chromatic dispersion is actually a distortion of the pulses. So what we're showing here is a sine wave that starts out pretty nice on the left-hand side, but as you go through the optical fiber medium, the sine wave expands, the optical pulse expands. The far end receiver is unable to differentiate, is that supposed to have been a 1 or a 0, or what am I actually sending? So this leads to bit errors if we don't accommodate chromatic dispersion. Some of those prior slides showed you the dispersion values for the different fiber types. And then the last one here, which is really the most kicker, is the OSNR, or optical signal to noise ratio. So just like in the RF world, we have signal to noise ratio, exactly the same. We've added optical at the beginning, but you know, we'll look at this a little bit, but you know, Brad, the interesting thing, the source of the noise in these environments is actually the amplification. So an erbium doped fiber amplifier actually adds noise as well as amplifying. So Brad, what was one of the analogies we talked about with that?
I think we were talking about how loudly a person can speak.
Okay, yeah.
How good someone's hearing is, right? If I were to slow down my speech and kind of make it quiet, some of you are going to have to listen in. So that's a really good analogy to understand what kind of budget is available for hearing a signal. And we want to make sure that I speak loudly enough to where if everybody in the audience starts talking, I can see what Kent is saying so I can hear him, right? If those two noises are close together, I cannot tell what Kent is saying, right? And that's an analogy for SNR.
Yeah, we'll go through each of these, some separate slides as well, so.
Kent, I think this comes up quite a bit of time, right?
Yes.
So we look at different optics, different pluggables, transceivers, and we know that some go 500 meters, some go 2 kilometers, some go to 10 kilometers, and you go in an ER optic goes 40 kilometers. But what is the actual math behind optical budget?
It's pretty simple, right? We would go to the data sheet oftentimes of our optics. We would look at the minimum transmit or launch power. In this case, we've said it's minus 10 dBm. So it might have a maximum transmit power of minus 6, but we really shouldn't use that because it could be minus 10. So we would use minus 10, and then we would look at the lowest receive power in that specification sheet as well. And in this case, it's just simple math. We launch at minus 10. Our minimum is minus 20. We have a max budget of 10 dB, Brad.
Okay, let me make sure that I got this right. So I'm going to the data sheet. I'm getting the worst transmission, right?
Yes.
As quietly as I can speak, and I add that to the best hearing on the other end, which is also in the data sheet. That's how I come up with it. Okay, so now that I understand how that's built up, how do we get the distance out of these?
Well, hopefully, you know, we have things like your fiber provider has given you the actual loss from an OTDR measurement, or even better, a laser source and meter. But oftentimes we do not have that data. The network is being built. Maybe the fiber is not fully constructed yet or spliced together. So we would use a value per unit of kilometer of a quarter dB. You might decide that you would like to use 0.22 dB in your environment, but this is really a safe value, a quarter dB of loss per kilometer for 1550 transmission. With a 10 dB budget and a quarter dB loss value, we could go 40 kilometers with this set of optics is our calculation here.
Okay, great. So this is good, standard, clean math. What about this stuff in the blue? I mean, anytime we put in some sort of a component in between of our transmission, whether we're splicing a cable, whether there's a connector, we're going to lose some of that power budget, right?
Yeah, good point. And a lot of times, you know, the quarter dB per kilometer can accommodate most of these unless they're really egregious. problems, but just listed the source of optical losses in your networks, right? Micro and macro bins, can be problematic and cause excess loss. The other one is contamination on the optical connectors, right? That's why it's very important to clean those, especially as we get into higher and higher speed optics, Brad. Very important to clean. There's really nothing we can generally do about the fiber attenuation. That is in the ground and likely will not be changed. There might be bad splices that we can go request our fiber providers to fix. There might be excessive patch panels, but generally we're not going to improve the fiber loss that's in the ground without changing something about that fiber.
I think that contamination piece is huge. I mean, I've seen so many engineers that basically pull out the jumper cable and wipe it against the finger and think that they've cleaned it. And please don't do that. A very bad plan. Lots of oil residue on your fingers. All right, so the quick math, top right green, that's a reference slide for you to just kind of refer to this. But again, if you have been dealing with the optical budgets and the calculations in the RF world and such, it applies here. What are the rules that we want to point out here?
A couple things with this one that I want to just point out. We oftentimes dB, dBm, we mix them up, we say them wrong, it's backwards. We're not really meaning, we're meaning the other one when we say the second one. But fiber loss, that span loss is expressed in dB, but the transmit receive power is expressed in dBm. dB is decibels, dBm is decibels milliwatt. The other thing that, Brad, we want to think about here in this scale, dBm is a logarithmic scale. So 3 dBm is actually double the power of 0 dBm. So every time you take it up by 3 or down by 3, you're doubling or you're halving the power. So we kind of forget about that and we don't, well, it was -10, now it's -13. We've actually reduced our power by half when it went to that -13. So that's, we oftentimes don't even realize or think about that.
I think coming from the decimal system, that's a trick because 3 is a small number, right?
Yeah.
But the logarithmic scale that has been invented to help us overcome these large numbers that break human brains, just be aware of that 3 is a big
number. Great reference slide to use.
Yep. Okay, back to the dispersion.
Yeah, we got a couple slides on this team. So again, as we talked about earlier, if this is the transmitter side over here, as it goes through the optical fiber medium, it starts to look like this. This is problematic to the receiver. So the beauty of dispersion, though, it is linear. It is based on the length of fiber, the type of fiber, and we can calculate this pretty easily and quickly. So originally when we started doing 10 gig type networks, we had to put in things like dispersion compensation modules or dispersion compensation filters right here, DCFs. But this is just fiber that we'll see in that next slide, Brad, to accommodate this. Let's go on to that next slide to see what this is. So this is a dispersion compensating unit right here. All it is a spool of fiber that has the opposite effect of the outside plant fiber. The problem with it is lossy because it is a fat spool of fiber inside of there.
So a little bit like what, 50 kilometers, 200 kilometers of fiber?
Well, it depends on the actual distance. It wouldn't be that long, Brad, necessarily. We'd like to space these out in the network, so we space out the losses of them. But inside here, these things would be pretty heavy devices. They're completely passive, which is a beauty. They do actually compensate for all the channels in our network. So if we had 40 channels of 10 gig, we use dispersion compensating units. They compensate for all 40 channels together. So that is a beauty. The downside is they actually add loss that we have to make up with additional EDFAs or amplifiers, which are the source of our noise, and then thus our optical signal noise ratio is even worse.
What are you showing in the fuzzy and the clear picture?
Yeah, these are eye diagrams of the optical pattern. So over here, before the dispersion compensating unit, it's a lot of fuzzy, but then after the filter, it really comes out really clean. This looks out of focus is the best way to think about it. That's really what's happening on the eye diagram. After the DCU, we come out really clear.
Okay, so nowadays, the most advanced technology is coherent transmission. Can you tell us what that is and how it differs from the direct detection methods?
Well, a couple things. First of all, with coherent technology, we do not have to worry about the dispersion compensating units anymore. The main reason is we overcome those impairments of dispersion inside the DSP, inside electronics. So we take it from an optical domain up here in the 10 gig world, we move it into the electrical domain with DSPs. So actually in a coherent environment, we prefer we don't even have DCUs in the network at all, and we just do, with the DSP is able to accommodate thousands of kilometers of dispersion. We're gonna see that here in a demo coming up, Brad.
Okay. Okay, how does that come into play into the SNR topic?
Yeah, the last one we're gonna talk about today is OSNR. So down here at the bottom, this is our noise. The noise increases every time you amplify noise at the next EDFA or amplifier, it gets worse, worse, worse.
EDFA.
Erbium doped fiber amplifier, right, Brad? You know your periodic table,
Correct.
right?
Yeah, that's a pretty interesting thing that you can look up on Wikipedia. Go take a look at the atomic element number 68. It's erbium.
See, he even knows
and its
the
discovery led to what excitement of photons. And so
Yes.
when you're able to deliver erbium component to the photons, the light shoots further. It's a pretty incredible discovery for us. So EDFA is one way to amplify optical signals.
But just like in your stereo at home, you get a radio channel that's very far away, you got some static in it, right? You amplify it, oh boy, it's even worse, right? So just in this domain as well, the optical domain, the more we amplify, the worse the noise will get, and then we will break the OSNR value of each and every optic. And those are published values as well, Brad, so.
Good. Okay, what do we have as our last resort?
All right, if we cannot accommodate with either of those techniques, the OSNR is so bad, we can do things, the last resort oftentimes is regeneration. And you might have heard this, the 3 R's, right? Reshape, retime, and reamplify. This is a back-to-back DWDM transmitter receiver pair that's connected together that actually cleans up the signal. It comes in like this, it would go out like this, retimes it right correctly, and reamplifies. It comes up much wider peak, if you will. But it's the most costly. We want to avoid this in DWDM environments. So this is the least cost, the most cost, and the least preferred option to use.
So this would be like us putting routers or transponders in line in a daisy chain to be able to propagate the signal further.
Maybe at a small site in the middle of nowhere, we have to do that, Brad, and that's very costly. But we can start to do that in routers and become more advantageous, as we'll see here.
Okay. All right, on to the DWDM components. This is the list that you should know what these do. We will go through them. We have slides for each of them. The two that I would like to call out right away is that EDFA or EDFA, if you want to sound cool, and then the second one is Raman. What is that, and what is the difference? They're both amplifiers, but what's the difference between them, and how likely is our audience to see each of them?
EDFAs would be 95% of the amplifiers out there today. When an EDFA is no longer able to amplify and we need even more signal boost, we might add on Raman amplification as well. It is expensive, so we prefer not to do it only when we need it, but we always do EDFAs first. Raman is actually a person, a physicist, right, Brad?
I think it was, an Indian physicist that got a Nobel Prize for discovering the light scattering phenomenon 100 years ago,
Raman was his name, correct? So this Raman amplifier actually works. Generally, they are deployed co-propagating either way into the fiber, and they're actually able to stimulate the photons out in the outside plant fiber environment. So they actually shoot out either directly with the channel or opposite to the channels being received, and they stimulate the photons in the outside plant fiber. So they're more expensive. They're really not deployed in a metro environment unless we have no other option.
Let's go over their components.
Yeah, this is the simplest one, right? We've got a DWDM mux, demux, and you know what the beauty of these guys is? This could be an example up here, 64 channels, so it have 64 individual wavelength addressed or frequency ports that you would plug into, and it has a pair of fiber going out to face this outside plant fiber. But one of the beauties of it is the mux and the demux can actually be the exact same thing. A mux just takes in the sources and multiplexes them together to a common fiber output. The demux just does the opposite. And as I mentioned, they're exactly the same device. The demux would take all of those channels and break them into their individual wavelengths or frequencies here, and this would go to the receivers. Now, what we've not shown here is you generally do this in the opposite direction as well, and this here is a mux and demux combined, so it's a bidirectional device.
So different colors or wavelengths, frequencies
Yep.
into the composite signal and then split out on the other end.
Correct. And the mux-demux team is one of those lost devices that we had in one of the prior slides, right? We don't get this capability for free, of course. There's specified losses at each end here that we will have to overcome if we do not have enough optical budget.
Okay. Next one is a ROADM. Now, that's
Yeah.
a mouthful to say. What is it, Ken?
Reconfigurable optical add-drop multiplexer. So we're able to reconfigure each and every wavelength to do different things. If we looked at that prior slide, all the wavelengths coming in on the left were multiplexed, and then they were demultiplexed on the right-hand side. Well, what if we wanted to carry that wavelength or frequency on past that site? It's hard to do in that environment. So that's where the ROADM came in and really revolutionized how we would provision services in our networks.
I think ROADM is one of the harder concepts, for me at least, was to grasp. But I think the easier way to think about that is a wavelength switch. Is that right?
Correct. And that's actually what is embedded. And you'll notice on all of these is WSS, wavelength selective switch. Exactly right, Brad. We're just switching and selecting wavelengths on an individual basis and doing the task at hand with each and every one.
I think the term that comes up quite often is the degrees. What are the degrees?
In this example, we have degree A, degree B, and degree C. So this means they face different directions leaving a physical building most of the time. This would face your outside plant fiber. So in this case, we have 3 degrees named A, B, C, and this ROADM device is able to pass wavelengths from B to C, C to A to B, and all the permutations out there. So that's what it's advantageous to do. In this example, we have 2 different ROADM architectures. So broadcast and select is the one on the left. It is the original one. There might still be some deployments out there with it. Route and select is more prevalent today. It's the one on the right-hand side. It adds a second WSS here. Just like the bullet says, it is added on the ingress of each degree, whereas over here, we're just splitting the optical channels, and this splitting eats up a lot of power budget to do the optical splits. So we're splitting the wavelengths or channels to all the other degrees. Okay, so exactly what I said, the ingress from each channel is passively split, but whereas over here we route with this route WSS where that wavelength or combination of wavelengths need to go to the other degrees, or maybe it's a drop wavelength as well. The other item here, the MUX WSS blocks all channels not intended for this wavelength. We'll see this in the next couple of slides, right, Brad? Same thing over here, the MUX WSS selects any combination of waves per the user provisioning. So as I mentioned earlier, you cannot continue to add these optical splits, right? Every time you do an optical split, you're losing 50% of your power. So we cannot keep doing this. This is one of the downfalls of this architecture, is accommodating these losses of the splits. So that's why this one is really prevalent today, because it preserves that OSNR by having less EDFAs. The other thing that this guy does down here is it enables omnidirectional, so a lot of different degrees. You can pass wavelengths from down here at the bottom out any of the degrees, and then it oftentimes adds a colorless infrastructure here as well. Remember how we said the MUX-DMUX has 64 wavelengths or frequencies stenciled on it, and you must provision those to be the same? A colorless add-drop device is actually, not specific. You just need to have a unique wavelength here, oftentimes inside of this device, but you can change the wavelengths later without changing the optical fibering.
Well, I think we're ready to show these folks the ROADM card, which you see at the right top of your screen. And also remember, this is that complex picture that I showed you at the very beginning that made very little sense. So now with the knowledge that we've shared with you today, we're going to take you through that picture, and I bet you will be able to understand exactly how ROADMs work. So it looks very complex right now, Kent.
Yeah, we call this the simple ROADM. This is the broadcast and select one, the one on the left of the prior diagram, by the way. Let's break this up, though, a little bit into the different functions. So first thing we got to think about is looks more complex than it is. The card, over here is a west card, so it is a unique card. Over here is an east card, so these are two separate cards. So first of all, think of it that way. These two cards face two different optical paths. So we would call this guy a 2-degree sight. It comes in on the east and the west. Let's build this guy out. We're going to first look at a pass-through wavelength. We said, hey, we want to pass the purple wavelength through our network. So what happens is we go through that optical splitter right here, Brad, that we talked about earlier, and it gets dropped to the DMUX, and then it goes over to the adjacent WSS complex.
I think, Kent, these terms, the ROADM itself, add-drop multiplexer, and then the pass-through and add-drop. Those are important concepts.
Correct.
I think one of the things that helped me make sense of that is thinking if you've ever been on a train in Manhattan, there are the trains that take every single stop. They're called local trains. And then there are also express trains that skip stops and dump you somewhere else. Is that a good way to think about pass-through, express, versus add-drop, stopping at every single site?
That's a perfect analogy. You're on the same train tracks, right, Brad?
Yep.
But sometimes you got that express train that goes straight through, doesn't stop. That would be these purple wavelengths.
Okay, it's passing through.
Yep, the other times that train stops, a different train actually, right? And we'll look at that in our next set of wavelengths. Okay, so what we're simply doing here is this WSS is saying, hey, think of this as a 1x2 switch on every wavelength. So if this was an 80 channel, a 40 channel, a 96 channel type network, this 1x2 switch here just allows this wavelength purple to pass through and go out the eastbound side. We would do the exact same thing on the westbound, and it would go out that way. That is all this ROADM is doing in this simple environment. Remember, this is the broadcast and select. So this guy down here is selecting it and passing it through. So the red wavelength is exactly the same as the purple and being a pass-through wavelength. Let's look at the other combination where we want to add drop a wavelength or a frequency.
That's the local train.
Yeah. So same thing, the services originate from the far ends, for example. In this case, we are saying the wavelength is dropping in both directions, east and also west. So we're dropping that same wavelength or frequency, both directions, team. So in this case, we would go to that splitter, we would go to our DMUX. The DMUX would be physically fibered to a specific receiver. This would be a DWDM receiver right here, and we call that wavelength number 3. Do the same thing over here, wavelength 3. And then for the transmit, this is the transmit of this particular host device, comes down to this add port, and instead of being switched this way, we add it and it goes out this way. The other key to this is we're blocking the pass-through channel that comes over here from going through. So this is where we're blocking right here. And then this guy goes out. We do the exact same thing in the other direction. And now this green wavelength or frequency is being add-dropped both directions of this 2-degree sight. The blue frequency does the exact same thing. Put them all together, we've got both. We've got 2 wavelengths that pass through, 2 wavelengths that add-drop. Brad, the beauty of this is we would have lots more wavelengths likely, right? And what happens when we want to change, purple to do a different function? Today, purple is pass-through or express. We could change purple to be an add-drop wavelength in the future.
That's why reconfigurable.
A good point, yeah. Come back
Good
to
stuff.
the name.
That's ROADM, a wavelength switch. Okay, terms such as crossponder, muxponder, transponder, how do I make sense of them?
Well, we mix them all up, right, Brad? It's another one of those terms. We say something, we mean the other. But let's just kind of break them down into 4 different scenarios here. Alien, we oftentimes say, hey, you got an alien wavelength. That it generally means it comes from a third-party source. It's not embedded inside the optical line system. It may be from another vendor. We call that alien. It could be anything. Brad, it could be the pluggables that we have up front here, right? That could be an alien source. Over here on the muxponder, this takes many clients, multiplexes them together to a DWDM frequency of your choice. As an example, let's say we have 10 gig E's here that are gray. We want to multiplex those to a 100 gig trunk at the DWDM layer to go out. Transponder, this is a 1-for-1. So maybe we have a 400 gig E client from a router, and we need to transpond that to a wavelength of your choice right here, and it goes out 400 gig. Now the crossponder is really a catch-all of a lot of different ones. This could be a layer 2. This could be, an OTN type device, but a crossponder can set on both east over here and west over here. Set them backwards, this would be east, that would be west. But it can bring in clients and then direct which way they go out the network. So we could oftentimes call that a crossponder.
A lot of times the devices almost are the same. They fulfill different functions.
Yeah, so right here we have a card. It can do all these personalities just with software provisioning. So kind of interesting, right? So we oftentimes say that's a transponder. We may mean it's a muxponder, but that's okay. So just maybe lay these out a little bit for you guys and talk about them a little further.
Okay, Kent, this is a very interesting slide. Can we kind of quickly cover why we're including it here?
Yeah, and we named it brief, right, Brad? Because we're not going to go through this, but I think a lot of times we hear QPSK, we hear 16 QAM. What the crap does all this mean, right? We don't know. So just a great description here of what the acronyms are. The bits per symbol would be right here. The top one would be, let's just say this is a 10 gig on-off keying. So every time we send a bit, it's only, once. There's no polarization of it. So we're only getting 1 bit every time we turn on and off the laser. But really to increase the amount of traffic in our networks, we're going to things like QPSK or 16 QAM. And that really starts to double, quadruple. You'll start to look here at the number of bits we're able to transmit in the same medium at the same time. We say these are polarized, this is a good reference of this, right? They're in different planes, so we're actually transmitting 2 bits at the same time at least with this polarization. But if we look at the constellations out here of QPSK, there's 4 different options. That makes sense, but you're sending 2 bits at the same time depending on which one they are. 16 QAM has 16 constellations out here where you're sending 4 bits. So you got to send all variables, or you have to have the option, to send all of the bit variables. So you start out here as 000 is up here on the left, and then you'll go down here 1111. If the next 4 bits were the same, you would transmit on this plane right here. So good reference here, but just a great way to maybe understand these in a quick brief without going into a PhD in physics.
It looks to me like a lot like the RF environment. It's all about how many bits we can put on the air to increase our transmission.
And guys, this is the exact same terminology, right? One is in the air, and even in the cable environment, right, Brad? The RF inside, the cable environment is very similar.
All right, fantastic. So now we've had these bulky optical line systems for a long time. They're still out there. You're going to see them for many years to come. However, what's taking place today?
Well, a couple things, Brad. You held up one of the DCO pluggables that we'll talk about here in a minute. Oftentimes, these transponders, muxponder, chassis, devices, they are taking gray optics from routers, transponding those to a wavelength of your choice, and going into a DWDM frequency to hit the optical line system. So let's take a look at a couple different options. This is the NCS 2015 from Cisco. It's got 15 slots. It can do up to 8.5 terabits of transponding, muxponding capacity. Look on to a little newer generation. This is 2RU, can do up to 12.8 terabits of capacity. So really a great improvement from a size perspective. By the way, look over here. What if we started putting the DWDM coherent optics directly into the router, which we needed anyway in most cases? We can start to save all the power and all of the real estate that these devices take.
That's the beauty of it. So that's kind of my territory, right? That's a Cisco 8000 Silicon One router, 12.8 terabits. We can fill up 32 ports of these 400 gig pluggables. That's pretty amazing how far the technology
And that's
is,
where the technologies are merging together, right, Brad, that we talked about at the beginning.
Yep. All right, so now, even though you do see a lot of optical systems still out there, and you will see it for years to come, nowadays routers are able to be the hosting space for the DWDM technology. So I think this is the slide that finally put it together for me. We have two routers that are, let's say, on the opposite sides of a metro area. We take in these pluggables, we put them into the ports, we run them through the MUX, DMUX, and then we amplify if necessary, right? Because we'll cover distances in a minute. We come out on the other end, and that is the entire setup, right? If you do not need the amplifier, these can be connected directly. Is that a clear picture of what is possible today?
That's perfect, Brad, and that's exactly right. We are just using the EDFAs to cover a further distance in our optical fiber plant to get to the desired other end, right? The EDFAs might be hosted in something like this, a 1RU NCS 1001, or we have some other options that we'll talk about as well, right?
Yep. Okay, so Ken, tell us about these pluggables. I mean, we're showing them the 400 gig pluggables. They're now going 800 gig.
Yeah, and we oftentimes mix up all these terms, right? ZR, ZR plus, you know, we're actually talking about them differently. So I wanted just to create one slide to highlight all three of them at the same time. So let's start over here with 400 gig ZR. It is actually an OIF standard interface. Many vendors make these. This is not just Cisco. But we call this access to metro networks. They can support up to about 120 kilometers. They have a CFEC, which is a lower performing FEC schema than these guys over here. This is OFEC. So just kind of when you see these, just remember O is higher than C, so O performs better. The transmit power of these guys is about -10. Remember that span budget calculation we looked at where I said the minimum transmit power is -10? That is these guys right here. But what we said, hey, in the DWDM environment, we need some better performing optics. So this OpenZR Plus multi-source agreement, or MSA, was created and formed with Cisco and many vendors. We're not the only ones. And 400 gig ZR Plus was formed. So we can do all kinds of different things. We can have different trunk rates. Maybe we can't cover 400 gig because we need to go 1,500 kilometers. So with the same pluggable, we can downshift to a 300 gig trunk rate and carry 3 by 100 gig clients inside of it, if you will. But at 400 gig, we can support up to about 1,400 kilometers. We're going to actually do a demo here in a minute, Brad, of 1,200 kilometers. The transmit power stays the same at -10, but this is where the third one comes in, which is the 400 gig ZR Plus Bright. It has a transmit power of 0 dBm. In a DWDM environment, most of the deployed networks out there today, they want or expect a closer to 0 launch power into it. So that's how this pluggable at 400 gig can launch 0 dBm into that DWDM line system that's out there.
Great. Okay, when it comes to distances, what is it that we can let our audience know that they can quickly remember?
Yeah, let's look at 3 scenarios, Brad, here. The top one is where we want to put 400 gig pluggable over a pair of fibers. So we'd say that's single channel. With ZR, ZR Plus, this is where you get your 10 dB span budget here, right here. Unamplified, dark fiber, point to point. Okay, if that's good and that's all you need, that's great and you can do that. But oftentimes we want to say, you know what, we need 2 channels or in 6 months we may need a third channel, a fourth channel. So let's put in some infrastructure that we've talked about here, whether it just be a simple MUX, DMUX type network, right? And then we can go about 120 kilometers with amplifiers at each end and MUX, DMUXing 400 gig ZR, ZR+. If we want to go even further, and we'll look at that in the demo here in just a second, we have line amplifier sites in the middle. We can go up to about 1,400 kilometers. We can also downshift to lower trunk rates and go even further.
What about the bright ZR+, the one that is 0 dBm?
Yeah, you remember the guy that launches at 0, now instead of launching at -10, we go 0, so we get 10 dB more of span budget up to 20. Let's just say we can go about 80 kilometers with this guy on a pair of dark fiber.
Is it twice as expensive because it's double?
It's not twice as expensive. It could cost a little bit more, but by no means is it twice as expensive. Single channel and multi-channel networks, whether it's a single span or multi-span, they're really about the same with the Bright ZRP, the 0 dBm one, but we do have a little bit better OS&R budget to work with this guy.
That's really nice. This is also an interesting application of these pluggables. What does this one do, Kent?
Okay, Brad, so we have it up here as well. This is taking the amplification and putting it into a QDD pluggable as well. So this does a pre and a booster amplifier, as shown right here. This faces the outside plant fiber. Here is a booster that amplifies outbound of the site. Here is a pre-amplifier embedded into this QDD OLS module. It amplifies inbound to the site. Out here are other ZR, ZR+, Bright ZR+ optics. They would set out here. So maybe we would have a router host device. We would have the pluggables that we've talked about in the prior slides. And then we could do this amplifier to cover, up to about 120 kilometers without adding any other network device into our infrastructure. So take the pluggable amplifier plus the pluggable coherent optics, and you can have a DWDM line system all in a...
That's pretty slick. Cisco buried an EDFA amplifier in this form factor.
Trying to continue to reduce the amount of equipment out there, right, Brad?
Yeah, and that brings us to this slide here. So in the past, what did we have?
Well, we looked at that up here. We'd have a router, we'd have gray optics, fiber jumpers, gray optics into a transponder, muxponder. We put it into a shelf. We do a DWDM frequency provisioning in this shelf. We go out a ROADM or an optical line system. With those pluggables, we can skip all the pieces in X and then put the DCO pluggable right into the router or the host device and go out the network.
All right, that's quite an improvement. Really quick, this is an interesting slide because it talks about the optical versus IP protection. Notice that in this slide, there's no one magic way to do things. You always give up something and you always gain something. So take a look at that. Here we've put up an IP protection at the top of the list right there on the right-hand side. If you would like for us to add some red categories, we certainly can. But this topic has a great coverage in the previous Cisco Lives. If you go look by any of our last names, and we talk about optical versus IP restoration and protection. And with that, Kent, I think this is the star of the show.
Yeah.
The demo itself.
Let's get into a quick demo.
And in the demo, it is basically DWDM technology in routers by an optical guy.
So what we have here is an NCS 2000 network in a Cisco lab, 1,200 kilometers. It has 12 spans of 100 kilometer of fiber each. So what we need to do first is we need to provision an LMP, or a link management protocol. This is telling the optical control plane that, hey, I'm a 400 gig channel. We're going to do that here in just a second. We're choosing the ports that we're connecting to. So we'll do that. We're going to put it into a little bit quicker speed here. Right here is where we provision our 400 gig. We're going to choose QDD, 400 gig, right? ZR+. We're going to set the FEC as OFEC. We're going to do the same thing at the other end, which is down at the bottom on site 6. We're going to speed it up just a little bit. I'm not actually that quick, but we didn't need to see this happen twice. And then from there, we're going to go into circuits, and we're going to create an optical circuit between site 1 and site 6 down here. So site 1, we're going to drag a line to site 6. We're going to say it's a flex circuit because we want a 75 gigahertz circuit. I've pasted in a name in there. I'm going to set the frequency right here. And I'm going to say it's going to be fixed because the router DCO will be provisioned with the exact same thing. Now I'm going to choose the LMP ports that I created previously. I'm going to include this optical side out here as well. And then I'm going to go ahead and hit create. So it's going to start to come up and it's going to create this optical path along the 1,200 kilometers. And what we need to do after this guy is up, you'll notice we'll get into the router up here at site 1 because it is not provisioned. So we need to provision our host router, which is an 8201.32FH. See, we have an alarm in our optical network because now we have a circuit with no input power. So we'll look at this a little bit. Now here is our circuit. You'll notice the carrier here is 60.14, and then the wavelength is a 75 gigahertz spaced wavelength. So let's get into that router up there at site 1. I'm going to go through some pieces of it. Right here is our 400 gig bright ZR Plus optic. Here is our router, 8201.32FH. We're going to do a show version right now, and this guy is running 791, which has been around for quite some time. This is not,
Last year, yeah.
some engineering code, right? So now we're going to start to provision this guy, and it's no big deal to provision the DCO pluggable. So we're saying, hey, DWDM carrier, 100 megahertz grid frequency right there, which is what we provisioned our optical circuit at. We're going to commit it. And then we're going to do, show controller optics 0004. And then I said summary. So right now it is receiving from the far end because it was always on, and I've started transmitting as well. So we're going to see this optical alarm start to clear once we started transmitting into our network. There she cleared. But one thing that I did incorrectly with the circuit creation is I intended to build it over this additional 2 spans up here. So I'm going to actually go into the DWDM software and I'm going to reroute this circuit to go not this direct path right here, but around this way right here. So I don't have to delete this or anything of that instance in this network, but I'm going to reroute it by choosing some different and additional optical paths. I chose that one, and I'm forced it to go through this one as well. And now we're going to reroute this guy over the 1,200 kilometers, because in this case, I wanted to show the furthest distance as possible. And remember, each of these spans is 100-kilometer spans. So get back into the router. Now I need to do something else. I need to change the the dispersion compensation parameter. So by default, it's set to about 13,000 right here. I changed it to 26,000 because this 1,200 kilometer span, we'll get to it in just a second. We're going to start at the top, but now everything is up, right? There's our wavelength and frequency of this particular port 4. Scroll down a little bit inside the show controller optics. We're going to get to the actual CD value right here. I'll highlight it. Yep. So we're about over 20,000. We accommodate that inside the DSP. There's no DCUs. So this is coherent optic, and we're doing it with a DSP. Here is that particular optic. Now let's look at show controllers coherent DSP. This is showing us our performance of it. We're about 0.7 of Q margin. So we have a lot of Q margin available. Anything, below half a dB or above half a dB, I should say, is pretty good performance. I looked at the other end as well, but hey, you know what? With the routers, we can send this into things like a Grafana, into a data lake and have Grafana pick it. And this is just a great way to see it, the parameters at each end as well. So there's our wavelength, 1556. Here is our OSNR. Here's our baud rate, which is set. And we're pretty much in business. Now what we're going to do is we're going to start looking at 15 minutes, seeing how it's going to run for 15 minutes. It's pretty good. It's ran 15 minutes clean, no uncorrectable words. Our Q margin right here is very solid. It's not changing any. We're going to look at the other end, do the exact same thing, and ensure it is operating. So this is something we didn't want to ensure it was working for 5 minutes and then quit. So inside the router, just like inside any transponder, we can get in and look at performance PM stats, and that's what I'm doing here. Now I've came back actually the following Monday, and we'll start to look at 24-hour stats inside the router. So we'll do 004, PM, current, 24, FEC, and look, now we can start to see 24-hour stats. We're in the current interval, it's about 23 hours right here. And then the uncorrectable words, so we've not dribbled any errors on this interface out there. So this is what we want, no uncorrectable words. We want it to be 0, right, Brad? We'll do the same thing at the far end. And from there, that runs through a quick demo of setting up the 400 gig DCO pluggables across an open line system, which has been out here for over 10 years.
Ken, fantastic work. Well, 60 minutes flew by really quick. What are some final words that you would leave our Routing Optical audience with?
Yeah, hey, DWDM not any harder. We encourage you to continue to learn about it, expand your knowledge. You know, if you're savvy on the IP side, you can pick this right up, right, Brad?
Yep, that's absolutely perfect. Don't be afraid to get started.
Yep.
We left you some good links right here. The question they ask from you is to complete your session evaluations. We live and die by these. If you like this session, you know, remember we're Kent and Brad. If you did not get anything out of it, my name is Raul. Give me a second chance this afternoon. I have a session at 3 p.m. here in the room nearby on network self-resiliency. So hoping to see you there, and enjoy Cisco Live.
Thank you.